A Beginner's Guide to Constructing the Universe by Michael Schneider. Has anyone read his book? It's very... if you just happen to be fancying to knock one up this afternoon. And this is all about, it's about maths, but it's sort of about form and nature, and it's an amazing journey. And if you're remotely interested in maths or even nature, then it's a fascinating read. So, highly recommended. And one of the things he says is, to understand nature better, we first need to recognise the roles of its basic patterns. So, as permaculture designers, or just quick hands, who's done a design course here? Yeah, so most of you. So I apologise if I say the odd thing that might go over your head if you've not done a design course. Maybe you grab the person next to you and go, oh yeah, that's what he's talking about. But to me, you know, as permaculture designers, what we're trying to do is to take advantage of nature's 3.5 billion years of research and development on this planet. Life has been spent a lot of time trying to figure out how to best live here and exist here and thrive here. And you know, we're quite relatively recent on the scene as human beings. And so as permaculturists, if we're looking for a great model for sustainability, then nature is it. You know, life, the diversity of life around us is it. And so as designers, permaculture designers, it's really important that we can understand how nature does that in order to design in a sustainable way and to mimic what nature does. And so Michael Schneider is saying that in order to do that, we need to understand the roles of its basic patterns. So we're very familiar, I'm sure, with, you know, picking up a shell off the seashore, or you know, and seeing patterns in all kinds of things, yeah, spirals and branches and so on. And yet what he's saying is, you know, what are they doing? Okay, they look lovely, they appeal to our sense of beauty, but they also have function. And so as designers, if we can understand what those functions are about, then that actually starts us on our journey to identify how we can fulfill those same kind of functions that we're trying to achieve in our design systems using those same patterns. Yeah? Because we see these things, we consider them to be patterns because we see them so often. And we see them so often because they are the best ways that nature has found to do particular things. Yeah? Does that make sense? I'll keep referring back to this, otherwise I go off on a tangent and I realise I've missed something I want to mention. So my own journey with patterns started with this book. Anyone read this? Anyone lucky enough to get a copy of this? The good news is that there is a bunch of them being bought fairly soon by Permanent Publications, the Permaculture Association and so on, so it will be available fairly soon, not just on Amazon for £1 million. But my own journey began with this book because when I did my design course, there wasn't much other than this book around. There's one other book here, which I'll mention in a moment. And this is Bill Mollison's Designer's Manual, but I'm sure most of you are familiar with. And interestingly, when I got this book, my teacher said, yeah, it's a great book, he says, but skip chapter 4. It's really a bit of a mind thing. And chapter 4 is all about pattern understanding. Yeah? Anyone actually read this or tried to read it? No? Okay. Good. Hopefully this will help. So a lot of people get stuck at the core model bit, which is this lovely diagram here. You can see. It's kind of like, oh, what's that about? Because he's trying to draw something in 3D on a 2D page, and I've yet to make this model in order to try and make this easier for my courses. But and so one day I kind of decided I'll skip that bit and I'll come back to it. And actually, once I got beyond that, and this baffling tessellation diagram here, which I still don't get what this is about. One day if I get to ask him, that'll be great. But it started to become really useful because, you know, here he is, and in his own words he says, you know, his patterns, this chapter is really him having an attempt at something he doesn't really fully understand, but he thinks is really important. And so, you know, it's for us as permaculturists coming into something that was started here 20, 30 years ago, to take permaculture and evolve it and to bring our own understandings to what is, you know, to me, something that could save us. Yeah. So patterns have function.
You can also get a t-shirt to go with the book.
It's quite rare now. So my first impression was like, oh, it's really scary, but actually we're completely hardwired to recognise patterns. You know, as a lot of faces in this room I recognise, And I know who you are because my brain is able to recognize the pattern of your features and store them. And that's really important to me in terms of my survival, because if I couldn't recognize the difference between somebody who was a friend or likely to kill me, or pick up an apple and know that it's safe to eat this, because my mother gave me one once and she knew it was safe to eat. However that pattern gets into our brain, we recognize this is a safe thing. If we have to experiment every time that we're hungry, okay, let's look around again. I don't know what food is, let's eat something randomly. We're doomed, aren't we, as a species? So we're already really good at recognizing patterns. It's not hard, okay? Yes? So, this is why I introduce an assistant other than Phil. This is Pimple, who's come to help me today. Yes? And Pimple is? Penguin? Or a cuddly toy? In the pattern of a penguin, yeah? Or a baby penguin, specifically. And of course, you know, many have seen March of the Penguins. Yeah. So, if this was a real penguin, it would be quite smelly in here now. Unless you really like fish. So, but we recognise this, and it actually can create in us an emotional response, because it's such a powerful stimulus to us, the ability to recognise patterns and connect with our emotional being. So, patterns are easy. We just now need to figure out how to use them. Okay, so the next bit is thinking about who heard of the edge effect on their permaculture course. The edge is important, yeah? Yeah? Edge is quite important, yeah? The edge is the abundant place where everything happens, yeah? And so the thing for us to do here is to link, you know, what is a pattern? When we think about what is a pattern, when we see a pattern, the pattern of a hand or a tree, that pattern is actually the shape of the edge between two different things. You know, so my body is this pattern, it's the shape of the edge between my body, which is still a bit fuzzy as far as I'm concerned, because I think it finishes here, but I'm not sure it does, which is in constant interaction with the ecosystem around me. So I am an ecosystem of a whole bunch of, I believe, 2 trillion cells. Is it 2 trillion cells in the human body? Something mad like that, of about 80% of which are bacteria, apparently. So, you know, we shouldn't be too worried about bacteria, really. And this organism I inhabit, that my mind is aware of inhabiting, is very much an object, is a demonstration in the ability of cooperation, that systems can cooperate in a beautiful way in order to make the ecosystem as a whole function. And systems exist within systems. So if I was to say to you, you know, draw the digestive system, draw a digestive system, some of you might include all kinds of things like the nose, because it's about smelling food before you eat it, or your tongue or your teeth. And some of you might just draw a few little bits down here. And the reason for that is because, you know, where do you define the edge of that? Because then there's the blood, you know, the cardiovascular system and so on that has to support that digestive system. You take that on out of the body and put it over here, it's not going to last very long, is it? So systems interact with systems, and the edge between systems is really important, because that's where exchange can happen. And that within this ecosystem, energy and resources are constantly being exchanged. Yeah? So the edge is where that happens, and patterns that we see are the shape, the form of that edge. Yeah? So most of those edges most of those patterns have quite a lot of edge to them, don't they? Yeah, if you think of branching or spirals, if you think about the amount of edge there. Let me stay on track for this. Oh yes, okay. So, come back to Michael later. Maybe. Okay, so I'm just trying to get a sense of who feels they've travelled quite a long way to get here. Psychologically is good. Who got a bit bored on their journey, perhaps? Yeah? One or two of us? Yeah? Okay, so you were at home, perhaps, or some place of work, and now you're here. And within this kind of human thinking concept we have, we might express that as, you know, this is where we came from, A. Don't worry, there won't be much maths in this session. And this is where we are now, B. And I remember at school, at some point, somebody saying, you know, what's the quickest way from A to B, which is straight line. Okay, I'll do my best. Can't do it. I can't draw a straight line because I have no straight lines in my body. I am an organic, curvy. I can move very nicely in curves, that's easy, but straight lines are pretty difficult. So we don't see many straight lines in nature, do we? Any examples anyone can think of? The horizon is still a bit curved, isn't it? Yeah? So there are approximations to straight lines. You know, and sometimes you think, oh, light travels in a straight line, but actually scientists will tell you that light is like that, actually, or at least one part of it is, the wave function of it is. So straight lines are really unusual. Curves, we see much more in the way of curves. And this is because, if any of you have seen the story of Stuff on the video, where she talks about, you know, here's a linear system that we're trying to run linear systems on a finite planet. So we take stuff from over here, we dig it out of the ground, we make stuff with it, we sell it to people, and we throw it away. Yeah? We take it from here, and we throw it away here. And there's no connection between these two places. In fact, what comes out here is no use here anymore. Okay? And she says, she makes a very clear point that that's a rubbish system. That really isn't going to work. Literally is a rubbish system. And nature doesn't do that, because if you think about in nature things, when I say they're all constantly on the move, they're constantly in cycles, like water, for instance. Yeah? So water starts, it spends a lot of its time in the ocean apparently, but every now and again it gets evaporated by the sun, off it goes. And then it might fall on a hilltop or a mountainside, and as it does so, it then moves obviously under the power of gravity. So here's our mountain. And the water pools down here, and then it makes its journey all the way down. So if we're looking at it from the side, obviously that's not a straight line, is it? There's quite a lot of upping and downing. Well, I say upping and downing, downing a lot and downing a bit less. There might be an odd splash where it does go up a little bit, but mostly it's going down. Obviously the up bit is evaporation, so nature moves things around by the power of the sun. And water that's actually held in the landscape up here, when we think about storing energy, we usually think about batteries, don't we, electric batteries and things, but actually a lake on a hill or a mountainside is a massive battery, because this is solar energy stored in water, which then lands on the landscape and then has the ability to do work, which we might think of as, you know, driving a hydroelectric turbine or perhaps irrigating the landscape. But of course, as far as nature's concerned, or what water is doing, is bringing life to the land, because without this cycle, there probably wouldn't be very much life on the land, or it would look very different from how it looks now, yeah, because we rely obviously on the rain. So there's water's kind of doing that way, but if we look from above, we'd have a slightly different pattern, wouldn't we? We'd have this kind of thing going on. It might do a bit of that later on and then turn into another river delta down there. But again, it's not taking the straight route. And the important thing here is that nature is in no hurry. Nature is, you know, this water is in no hurry. And wherever this water is, it's doing something useful, whether it's giving life to the oceans or the land, or weathering rocks, which is creating soil down here and so on. So this concept really is, you know, it's great here, it's great here. We put up with a bit in between. This is your M25 commute every day. How do people do it? But while we're doing that, we are respiring, you know, and we think of the trees actually supporting us because they produce oxygen for us, but the trees also need us to produce carbon dioxide for them. So we're doing good work even when we think we're not, okay? Life is never doing nothing useful. So let's start looking at patterns specifically. So put this off for a moment. Ah, yes, the one thing I was going to do here, which might be slightly messy, and normally I do hand this around, there's no way of doing it with everybody. So we're looking at water here, but when it falls out of the sky, it's quite easy to think, well, maybe it falls in a straight line out of the sky, or when you pour it, water falls in a straight line. And I challenge you with this, with your beer, or whatever it is you're drinking later that you pour out of your bottle. I've been trying to keep this, it's been sat here for a while. keep it as still as possible. And all I'm going to do is, if you can see, I don't know, try not to get cake wet, we'll just pour the water and just observe what the water is doing as it falls. And also what's happening in the glass. Oops. Okay, so what do you see going on there? Spiraling, yeah? Yeah? What's that about? Why does water do that? And so water is a really weird thing, and I'm not going to get into water here because it's a whole other subject, but it has a lot of strange behavioural properties. And if it didn't have those, we wouldn't be as we are. This thing wouldn't happen on the Earth, and we wouldn't be here. So I kind of always think it's really important to appreciate the simple glass of water for what it is. But water falls in that spiralling form, and as it does so, what else was going on in the glass itself?
Bubbles.
Bubbles, yeah. So it's basically mixing with the gases, which is the air around it, and injecting that into the water. So as water falls down a mountainside, as well as doing the usual weathering, eroding stuff that we're familiar with, it's also aerating that water, it's putting oxygen into the water, which then allows life to live in the water. And of course, when it comes down here and it sort of sits and stays in one place for a while, what happens to it? It becomes stagnant, doesn't it? And then things die and you get anaerobic decomposition because there's no longer any oxygen in it. So again, water likes to also move. And there's a whole other thing around there from Victor Schauberger's stuff, which is really interesting too. So coming back to, now let me just give you a quick quote. Buckminster Fuller, anyone familiar with him? Yeah, see the geodesic, is that a geodesic dome? Is it? No, okay. So geodesic domes, like the Eden Project. He invented those and did loads of other mad stuff. And I just love this little quote here, and I've got a bunch of handouts for you at the end, so don't go without a sheet if you want one. And it's on here, so you don't need to write this down. He said, "Straight lines are axiomatically self-contradictory and self-cancelling hypothetical ventures."
Nothing complicated.
Which I think means they're a bit rubbish. So, okay, so coming to the forms themselves. So I'm going to start with the one that we're standing on, which is the Earth. Yeah, and what form is the Earth? It's roughly spherical, isn't it? Yes. Yes. We could get quite technical about exactly what shape it is, but you know, and I can't draw straight lines. I can't draw a circle either. Apparently, a genius can draw a circle perfectly freehand, but I'm working on it. Well, I need a second go at that one. So, and this is the most, in terms of surface area to volume, what is a sphere?
Smallest surface area to volume.
So, smallest surface area to volume. So it's actually the most stable form as well. So gravitationally, everything comes together and it forms that sphere, and that holds it nicely. So this is very stable. But because life is, and you know, the ecosystem as a whole, the Gaia hypothesis, if you like, is wanting to create conditions conducive to life, it might look quite round from space, but if you start getting in close, you can start to see that it's not quite as round as it appears, because of course, you know, we've just been talking about the mountains, so the tectonic plates, they're pushing up mountains all the time, they're creating extra edge. And of course, on the oceans, the wind blows across the ocean, creates edge, more edge, waves. Yeah. So nature is always kind of driving this basic sphere and turning it into something with more edge. And if you took our skeleton away, what would happen? We'd probably turn into a blob, wouldn't we? So our body actually invests energy in making a structure that stops us being a blob. Yeah. Which I guess must be useful. I guess as a blob we could roll around quite easily, but this gives us other opportunities. So, and we see spheres obviously when things are trying to protect themselves as well, or retain heat, like a cat curls up in a ball, or a woodlouse, or a hedgehog would roll up. Hedgehog does both things, it does a spiky thing as well as the round thing. But the sphere, But lots of, that's why I call it a hedgehog, an hedgehog. Yes. So, hello. So biodiversity. So what would happen if we broke that in half? No, I'm not talking about, this is not the Earth anymore. Don't worry, although that's slightly worrying. If this is a rock and we shattered it into several pieces, what would happen to the surface area on that rock? You'd have more, wouldn't you? Yeah, because basically you'd have what was on the outside, but then you'd have some that was previously on the inside. And what will happen to the surface area of that rock? What will life do to that? It will colonise it, won't it? You know, you'll get lichens coming along first, probably, and mosses and bacteria and so on. And eventually, whole ecosystems will evolve on those little pieces of rock. And as water comes along and gets in the gaps and freezes, and you know, that's another weird property, that water expands when it becomes ice. That's just weird. Nothing else does that. And yet, without that function, water wouldn't be able to weather rocks and break them apart. And as it does so, which, as a physicist, trained physicist, I remember my, it's really coming to join in. My lecturers, you know, entropy, that's a really bad thing because things are falling apart and we're all doomed. It's going back to doomed again. But I was completely puzzled by, you know, so why, if it's all falling apart, why is it all together in the first place? How did it get to be together if everything only ever falls apart? And of course, when I started to think about it, actually what puts it back together is, well, on one level, life, on a bigger scale, gravity. Yeah? So things float around in space and they start to stick together. Yeah? We still don't really understand what gravity is or how it works. Maybe it works to get people to convergences. And so as things fall apart, as entropy increases, so too do the opportunities for life. And so as things fall apart and get smaller and smaller, then more opportunities exist. And then what's the most fertile soil we can have? Yeah, or just in terms of its particle sizes, clay, yeah, very, very tiny particles, loads and loads of surface area, yeah. In fact, so much so that then the electrostatic charge on water can stick to it, yeah. So lots of surface area is better, and as things fall apart, then so does life have more opportunities to put things back together again. And so instead of designing things with low entropy like plastic bottles, which at one point sounded like a good idea, because you know other things break or cars rust, let's make things out of plastic. And then suddenly we're going, oh my God, there's 1,000 square miles of plastic floating around in the Pacific Ocean. What are we doing? So things falling apart is good, and if things didn't fall apart, then we wouldn't have the raw materials, life wouldn't have the raw materials to make new stuff with. And as conditions evolve on Earth, then, you know, apparently the sun is now 25% hotter than it was when life first appeared on Earth. So I'm told. I wasn't there. Well, sometimes I feel quite old, but I wasn't quite that old. And there was a very different constituency of the atmosphere. There was hardly any oxygen at all. In fact, it was a kind of a toxic gas to the bacteria that were around at the time. And but over that period of time, life has had to evolve to changing conditions on the Earth. And the only way it can do that is to always have some new stuff to make stuff with. So there was a guy who I remember was talking about artificial intelligence, and he was saying, yeah, basically, you know, where we're going with this is if we finally get to the point where we realise the best stuff to make artificial intelligence out of is what life already makes itself out of, biological stuff, because it can be infinitely recycled and never degrade. Yeah, so we're better than artificial intelligence. But that idea that, you know, nature's already done that experiment, and here we are to prove it. And so, where was I going with that? It's my intelligence has just flown away. Well, let's go back to this. Anyway, so yes, so this idea of things as they get into smaller pieces, this pattern's called the lobe pattern. And this is about you know, breaking things up, making more edge. And if you think about the bacteria that are floating around in your intestines, yeah, massive surface area, lots of bacteria, very small individually, but collectively, lots of surface area, exchanging nutrients with what's passing through your gut and actually giving you useful stuff, or at least the good ones do. the bad ones compete with, because they eat what you like to eat and they produce the same byproducts as we do. But this is happening all over the place. And if you go and you go and see a reed bed system with gravel, that's what the gravel's there for. The gravel has a lot of surface area. That's where the bacteria live. So this is good applied patterning in design. Okay. So let's have a look at a few other patterns just quickly. I've no idea what the time is doing. No, that's not right. Oh no, it's all right. I've got half an hour. Hello. Still there. So if I can just split you into chunky, groupy kind of things, somewhere around there, and maybe you group on the floor, and can I give you one at the back that you might need to coagulate around there somewhere, and one here, and if you can just one outside. And just in your groups for a moment, just do a quick brainstorm on where you see that pattern in nature. You know, there might be really small scale, big scale, hour scale. Yeah.
Well, I'm a bacteriologist, so I would say spiral, which is a bug. And I mean, yeah, I mean, this is
Okay. This is an effective pattern. I like this. I work with this. Is it interesting that has anyone got some of these at home? Yeah, they're very interesting. They're actually tuned slightly off from each other. So I don't know what the frequency is. Would this be 1,000 hertz or something in that region? Or thereabouts? Anyway, whatever they are. This might be 1,000 hertz. This might be 1,005 or 6. Yeah. And the idea is when you ting them together, you get a beat frequency, which is the wah, 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 wah. And what I'll do is I'll do it again and see if you can hear it. So. Yeah, you hear that? And so this is all about the principle of entrainment, which is if you put a strong frequency over a weaker one, then the weaker one will entrain, it will come into alignment with the stronger one. And there was a guy apparently who had loads and loads of grandfather clocks a long time ago. And he went out one day and they were all out of sync with each other and he set them all going. And when he came back, they were all aligned with each other perfectly. And however that works. But this is entrainment. And the idea is that when you ting these and your brain hears that between 4 and 8 hertz frequency, it takes you into that brain state, which is that calm, meditative place. So that's why these are associated with meditation. And why it calms down a busy group of people thinking. It takes you out of your thinking phase. So, yeah, if we go around very quickly and just get a few ideas from each group. So if you'd like to start over here.
oh, well, I mean, we had everything from sort of half a DNA molecule to plant spiral. Plants climbing, air currents, tornadoes. The way that people learn. Springs.
Yeah.
I came up with spirochete, which is sort of bacterium, as I'm a bacteriologist.
Okay. Yeah. So that's technically a helix.
Yeah.
Yeah. Great. Okay. Group at the back. What do you have? Okay.
Beehive, giant's causeway, rock, poppy seeds, dense plants, cross-section, insect eyes.
Yeah.
Stability. I think it's very stable.
Yes, it's very.
Reinforced
Yeah.
Over and over again in the same shape.
Yeah.
So there's great efficiency for the use of resources.
Yeah.
Cell structure
Indeed. Yeah.
as well as the other thing, and also the sort of like leaves and stems, so how water travels in the plant.
Great. Okay. Yeah. Thank you. Down here.
For our spiral, we came up with snails, fossils like ammonites, water, plant tendrils, certain flowers like Basilia, increasing speed, whirlpools, weather systems like hurricanes, the inner ear, a galaxy, and fractals. appearing in things like sunflowers and Romanesque option.
It's also the basis of human movement. Spine moves in spirals as we turn our
Okay.
head. All of the body's in spirals.
Great. Where are we next? Outdoor group? Pietro.
So it's flow patterns converging and diverging flow. So, for example, rivers, trees and tributaries, and nervous systems, the brain, and then out through the spinal column and out to the limbs. Come on, people help me. Roots and branches of trees, mycelia, the lungs for the breathing system. Family trees. So if this is a pair, you've got descendants or ancestors.
Yeah.
Anything else? There's a thistle. There's like certain types of plants.
Certain kinds of seed heads.
Yeah.
Yeah.
Yeah. Okay. That's good.
Yeah.
Okay.
We had squiggle,
and we're thinking snakes and worms and the patterns that they leave. Things like ripples in the water and waves, sand dunes, sort of wind effects like that. Fingers and digits. What were some of the other ones? An udder, cow udder. What were some of the other things? Yeah, intestines. Hair. Curly hair.
Great. Okay, thank you. It's not an ideal curve, is it? It's just you have to use your imagination with that one. Yes.
Call that woodlouse. Melon, orange. Was it magnetic?
Yeah.
Seeds, yeah. End on it will be a star.
Yeah. It's a kind of carambola, star fruit. Yeah.
What's that one called?
Well, it's kind of a sphere, but with extra bits, like a magnetic field around it, like around the Earth, and yeah. So, but yeah.
Citrus fruit and orange.
Yeah. Okay, so we've been talking about kind of where we see them, but also there's some reflection been coming out about why they're like they are. So Amanda, you were talking about diverging or collecting and distributing. And so when we think about that branching pattern within a tree, it's all about collecting and then distributing to the leaves, or collecting and distributing. There's that kind of two-way flow, or within our lungs, of course, and so on. So that's very much about what the function of that is, and creating extra edge. And interestingly, I mean, a tree, if you've got an acre of trees, for instance, fully grown canopy trees, then you've got between 40 and 400 times, between 40 and 400 acres of leaf surface area collecting sunlight. So that branching pattern is massively increasing the edge of the ability of the earth to harvest that sunlight and make life. Yeah.
It's also self-repeating, isn't it? So you just need a very simple code.
Yes.
Repeat it again and
Yeah.
again and again. It's smaller and smaller.
Yeah. And simplicity always wins out, doesn't it? Yes. So what else do we have? We had yours there. So that's kind of about cycles, isn't it? I mean, so you have to use your imagination to a degree, because that's on a flat piece of paper, and we're trying to imagine it in 3 dimensions, really. But it could be the Earth rotating, going around the Sun. I know that's slightly elliptical, but also the Sun is moving through space, so the Earth is actually doing that, following that pathway. And the DNA, people familiar with DNA?
Yeah, we said half a DNA. The DNA is a double helix. We've got a single helix.
Yeah, DNA is mad. Within the nucleus of every cell in your body, you have 6-foot long piece of DNA, and it's only able to get in there because of all the ability for it to wrap itself and coil itself. So, what else do we have? Yes, as you say, it's the most efficient use of resources to produce a strong structure. And you had spiral. What do you reckon to the spiral? What's that about? Any ideas? Yeah, so you think about water going down the plug hole or into a whirlpool, it's accelerating, isn't it? Or if it's going outwards, it's decelerating and distributing. So again, it's collecting and distributing, but there's a speed thing going on as well at the same time.
It's changing scale as it comes out.
Yes, yeah. What else? There was the wibbly one. That's another kind of, it's a wave function again, isn't it? So it's, on one level it's about making more edge, but creating opportunity. So we could be thinking about the seasons, time, day, night, light levels and so on with that one. And so we see all these things because they're nature's way of adapting to the situation that nature is finding itself in. And we often find them not individually, but collectively, in pattern mosaics. So we think of trees as having that form, but actually if you look closely at a tree, it also spirals, or has, well, I suppose it's a vortex because it focuses in on a point, doesn't it? And, but very often, unless you're looking at, your Salix tortuosa with really obviously curved, or your twisted hazel or whatever, most trees it's quite subtle and the branching pattern is more dominant. But actually if you look, the tree is constantly having to think about, it's designed itself or evolved to produce the next leaf, so it throws the least shade on the leaves behind it. So it's always looking for the next gap, so there's the rotation of buds, which creates that spiraling form. And in some cases, like a sweet chestnut tree, if people familiar with the bark of sweet chestnut trees, really, the whole tree goes, it's completely amazing. And so, well, within the leaf, it's always about throwing the least shade on the leaves behind it. So the new leaf doesn't want to shade the leaves behind it. So it's always looking for the next place where it can do that most effectively, if that makes sense. Did I say that well? Yes, so, and the surface area one's so really important. If you think about what oxygen exchange our body needs to have, apparently our lungs, surface area of our lungs is the equivalent of a football pitch, all packed into that nice little thing that, if we had to carry around a football pitch with us, we wouldn't be here. So we're only able to be the size we are because we can gather that much oxygen through such an efficiently designed structure. The inside of our colon is 250 square meters. And it does that by having what are called villi, this very much a finger-like structure going on inside. And each one of those villi has a whole bunch of other little ones on top. So it's a fractal again. It's a fractal being patterns repeating at a smaller and smaller scale. And mathematically, you can take that to infinity. But I think in the human body, it probably goes so far. And then if you think about what happens if we, people often have digestive disorders now, and it's related to food. But for me, I don't do particularly well with gluten, and I've only observed that as a pattern. I haven't been tested for that or anything, but I've just observed my pattern of eating things with gluten in over time, how I feel. And that's a really useful thing to do because you just get to know ourselves better as well. But when those kind of sticky glutinous substances get in between the fingers and get stuck in there, that massively reduces the surface area inside my gut to absorb food. And then suddenly the only surface area I have is this bit on the top. And I've lost all of that because it's full of gunge, yeah? So the body was designed to evolve in the ecosystem with the food around us, and we've kind of changed our food quite a lot, perhaps. And that potentially affects the efficiency of our organism, yeah? Body, some of us more than others, perhaps. So when we're thinking about patterns and their functions, it's also worth thinking about how we've been using those things up to now, and perhaps some of them are less effective than others. So we think about the road network that we have now. It evolved originally from paths and tracks, perhaps originally through forest and maybe cart tracks and so on. And what happens with a green lane if nobody uses it? It turns back, yeah, everything grows back, doesn't it? Yeah. And so those kind of systems are organic. Anyone here run or work out or anything? Yeah? So what happens if you stop training? Your muscles kind of go down again, don't they? So your body kind of creates things when it's needed, and when it's no longer needed, it recycles those materials and does something else with them. And that's an organic system. It grows and it shrinks depending on the needs of the organism. Now, our original lane network was like that. If lanes got used, they remained open, and if they didn't, they would grow over and they would disappear again. Now we put big lumps of tarmac everywhere. It's a lot more work for nature to try and get through that. Although excitingly, there are mushrooms that will burst through tarmac, according to Paul Stamets. So we have hope. But anyway, with that tarmac, basically you remove the ability of the earth to grow food or harvest sunlight, but also to recover. So, roads will break up eventually, but it will take a lot longer if we, once we stopped using them. So we created a network which is no longer organic, yeah. And so, so whilst we might be using those same kind of branching patterns, so when we arrived here, we might have come off the M25 here or something and gone into a slightly smaller road, an A road, and then a B road, and then Manor Lane, whatever. And each of these gets smaller because it has to deal with less and less traffic. And in an organic system, then obviously the less traffic, the more it gets overgrown again. Whereas in this system, everything is fixed. So the way we tend to deal with it now is, we were driving around and there was another lane or two going on the side of the M25. And what's that going to do? It might relieve congestion here, but then what happens? You have more traffic on here, so the congestion just goes somewhere else. So we're kind of using those patterns, we're not using them so well. Anyone here do a 9 to 5? Oh, well done. But, I was particularly aware a couple of times I've been to the Mediterranean, this kind of siesta culture where it's too hot, you just chill out for a bit. You start earlier in the day. It's much more kind of in tune with nature and, our ability to do work and to do stuff. Whereas here, it doesn't matter if it's the middle of winter or the middle of the summer, you've got to get up and go to work at 9. You come home at 5. Which creates more of this congestion, of course, because everybody's moving at once. And we're completely out of sync with the seasons. We even have a calendar which is broken into 12 when the moon actually goes around 13 times in the year. So everything, we have all these systems which actually take us out of the feeling of natural time and being in the seasons. And then it's no wonder that we kind of forget or don't know what food is seasonal anymore. It's scary. So, if we're kind of working and mimicking nature, then what we need to do is identify the patterns that will help us to do the things we want to do. So our strategy, let me see, where do I want to go with this? Yes, I've missed one. This is where I need a bit of room on the floor. I need 3 volunteers to be trees. Okay, so I've got a pine tree. Do you want to be a tree? A beech tree, oak tree, and a pine tree. Okay. Yeah. Okay. So it might be good if you kind of create a space in the middle so everyone can see and actually work in the middle. Sorry about that, everyone. Causing chaos again. Okay. Right. So what I'd like you to do as trees is you have seeds. And you have abundant seeds because nature produces loads and loads of those, of course. I'd like you to just scatter your seeds. Not too far. Oh, God. I was thinking loosely in this area here. I knew you'd be trouble. Okay. And this process, okay, what kind of things cause the seeds to be scattered? How would that occur? What's the mechanism of that? Winds.
Whether the seeds are built in sort of little springs or something.
Yeah, it's kind of twirly things. Yeah, birds, animals. Yeah, yeah. Okay. Yeah, animals. Yeah. So there's all kinds of mechanisms that seeds get moved around, and those seeds are obviously produced at different times as well, over a period of time. So they won't all appear at once like a nice GMP crop that you can harvest all in one go. That's right, you can sit down if you want to. That's right, try and sit around the outside somewhere. And because of that, of course, the wind will blow this way on this day and this way on this day. So seeds are scattered randomly. Sometimes it's what's going on in the mind of a cow. It's like, oh, I'm just going to go over there now. And it has a little... and leave some thistle seeds behind and whatever it's been eating. And so there's so many random processes that cause seeds to be scattered around. So if we were just to have a look here at our scattering patterns, what do we notice about the distribution? And we're only looking at 3 different species here, but how are we noticing their distribution? What's going on here?
There is clumping.
There's clumping.
Completely random.
It is completely random, isn't it? Or at least beyond the ability of my mathematics to work out. And so there are places where you have, there's a cluster, you've got beech and some oak and some cones here. And there might be other places where, okay, we've got a cone and there's not much going on in those oaks, beech. And then there might be areas where there's just oak or just beech or just cones, pines and so on. And so nature is effectively consistently playing the lottery. Yeah? So it's okay to play the lottery, as long as you buy all the tickets. Because nature always buys the tickets. And it doesn't matter that most of the time life loses, because there's always a winner in life. And this is what gets us around, this is what's got life around the fact that the environment around it has changed, that the sun has got hotter, that there are seasons, things move, climate change that we're facing. This is not the first time that life's faced climate change. For us it's a bit of a shock, but life's dealt with this a lot. And the way life gets around that is by constantly trying new experiments. And we're familiar with guilds. Anyone play around with guilds in their garden? Yeah, so clusters of plants or species that grow together well, that support each other, so very often a guild might have a particular plant you're wanting to grow, like a brassica maybe, and then it might have a nitrogen fixer because the brassica likes lots of nitrogen to grow, it's very leafy, so like a legume or something. And then you might put something else in there as well, which is about repelling the pests that might come, so, I don't know, a chicken. They would eat the cabbage white caterpillars, no. So normally it's a plant. Or it might be like a squash that covers the ground well and prevents evaporation in a hot climate, so mulches effectively. So we're putting plants together for beneficial relationships, and so this is nature just keeping on trying this, because whilst a particular cluster might work well for a couple of 100 years, but as the climate changes, then different combinations of species will actually prove to be better suited to the new conditions. So if nature just did the same thing over and over again, it would come to a dead end.
It happens every year.
Yeah, and so this is, this is the ultimate pattern, no pattern, on one level, which is kind of odd and paradoxical, but this is the way nature has managed to, or the way life has managed to survive on Earth. And this is a strategy that Fukuoka, anyone familiar with him? Pietro knows him well, yeah? Fukuoka? Fukuoka. Yeah, yes. It was his natural farming. And his strategy was very much about, scatter the seeds around the orchard randomly, just mix them all up, throw them out there, and then see what happens. Yeah? And allow nature, allow the vegetables to say where they want to be, because they'll thrive in the places they're happy and they'll struggle in other places. And so everything finds its own place. And that's great if you have lots of seeds. It's not so easy if you've just got a little packet and you have, there's only 5. What shall I do with them? So, but nature has loads of seeds, and a lot of this can be food, and that's fine, because even the squirrels, it's like, bury it, and they'll be planting more trees. So there's everything gardens. So, so the random scattering is also a pattern, and it's a really important overall pattern that nature has. So we can use this technology like, this technique like Fukuoka does, but only if we have lots of seeds. But I'm sure, once we get used to this idea that seed saving is a really good idea, seeds are real wealth, then that's fine, because then we get away from this idea that we have to protect every last seed we have from things that are going to eat it, because there's enough for everything. To create biodiverse environments where it's not just us saying this is our food and everything else must keep off, but that there's enough that the things that also need to feed from that space, which is the biodiversity, the web that connects us all. Which brings us back to that pattern of the web. Anyone involved in transition? Yeah? And how does the web relate to transition? Relationships, yes. So it's resilience, isn't it? Yes. The strength of a web comes from, well, certainly the flexibility, which interestingly again, look up close to the spider's web, and where the bits cross, they have these squiggles. They kind of tie these little squiggly knots, like this one here. So when something hits that, it stretches and then comes back again. But also the other point, of course, about a web is all the connections it's making to the outside, so where it's attached. This is the important part. This is what makes a web strong. And unfortunately, we're not on the outside of that, we're in the middle, which is kind of, hey, we're the spider, but actually we're in the most vulnerable place, because if some of these start getting broken, and we could relate these to the species that create life on this earth by harvesting sunlight, the green photosynthesizers. This is the plants and the trees. Well, to some level, but they're kind of the next stage up. But they do help the photosynthesizers. If we start destroying that biodiversity, we're weakening the structure of the web. And whilst we're in this web, we're able to feed from any energy and resources within the web. But if we start breaking the links, we destroy that biodiversity, we become more vulnerable. I'm sure I don't need to tell you that. But kind of the vision I have for that is on those old black and white movies where you've got the guy sawing a hole in the floor. And he's just not seeing what's coming. But that's just what we're doing as we destroy species, and we're not caring for the earth and the web in which we're a part. So, and a good web is one that basically harvests the resources it needs, but also allows the things that are going to burden it through. So a spider's web allows wind through it, because it doesn't want to be broken, but it's close enough together that it harvests the insects that fly into it and so on. We could think of ourselves as webs of a sort, a net if you like as well, this same kind of pattern, that we're moving through the environment, we're consuming things in order to nourish ourselves, to make ourselves stronger, and then we're passing on those resources, which is fine as an individual. But then what happens when we start building these things is, and this mind we have, because we can project into the future and we have the media that tells us we might run out of stuff, we start thinking, instead of just storing a few things for the winter like everything else does, or a bit of body fat, we start accumulating lots and lots of stuff just in case. And because we've got a nice big space, we can lock it all up, then that seems okay. But actually, if you go back to thinking about energy and resources like to stay on the move, when they're stuffed in our loft or in our cupboards, they're not moving. They're not available for other people to use. And this, of course, is clutter. Yeah? So clutter is not a good thing because it's storing nutrients and resources which could be used elsewhere more beneficially. And it means that we have to buy a bigger house to fit all the stuff into, which makes our life more difficult because we then need to earn money, more money to buy the bigger house and to pay the insurance, which is higher because the house is worth more, and so on and so forth. So, free cycle is a good application of pattern.